Out in the dark, quiet corners of the universe, there exists an object unlike any other. It is a celestial force of nature, invisible to the eye, yet mighty in its pull. The black hole. Its very existence challenges the fundamental laws of physics, bending the rules of space, time, and gravity. It is a point where the known universe breaks down, where all logic is turned upside down. For centuries, the black hole was thought to be an eternal prison, an inescapable abyss into which matter and light vanish without a trace. It is the ultimate enigma, a region of space where not even light can escape its grasp. But what if I told you that black holes were not eternal after all? That even the mightiest forces in the cosmos were subject to the laws of time, change, and even decay? This is the story of Stephen Hawking, one of the most brilliant minds to ever grace the field of theoretical physics. In the face of personal adversity, he became a beacon of human curiosity and determination. Though confined to a wheelchair by ALS, his mind roamed the vast expanse of the cosmos. It was within the depths of his imagination and intellect that the idea that would forever change our understanding of the universe took shape. In 1974, Hawking proposed an idea that, at first, seemed utterly impossible. That black holes, those cosmic giants that devour everything in their path, could actually emit radiation. That, in fact, black holes could lose mass and eventually disappear. His discovery of Hawking radiation would defy centuries of scientific thinking and set the stage for a new revolution in physics. Hawking's revelation was rooted in the very fabric of quantum mechanics, where the normal rules of our world are stretched and distorted. At this microscopic level, even empty space is alive with activity. Tiny fluctuations occur constantly, creating pairs of particles and antiparticles that briefly come into existence before annihilating one another, returning their energy to the vacuum. But near a black hole's event horizon, the laws of physics take a strange turn. The intense gravitational forces are so powerful that they stretch the fabric of space itself. This distortion can separate these quantum pairs before they can annihilate one another. One particle is drawn into the black hole, while the other escapes, becoming what we now call Hawking radiation. This escaping particle carries energy away from the black hole, causing the black hole to lose mass, little by little. Over eons, this energy loss could cause the black hole to shrink and, eventually, evaporate entirely. Hawking's discovery was not just about black holes, or even just about radiation. It was a profound shift in the way we think about the universe. The idea that black holes could evaporate, that even the darkest, most incomprehensible forces of nature could fade away, challenges everything we knew. For centuries, the black hole was thought to be a one-way ticket into oblivion, a permanent state of destruction. But Hawking's idea shattered that certainty, opening up new questions, new possibilities. Could the entire universe, like a black hole, eventually face a similar fate? Is everything we know ultimately subject to entropy and decay? And if black holes do fade into nothingness, what does that tell us about the nature of the universe itself? But perhaps the most fascinating and indeed humbling aspect of this discovery is the realization that even the most seemingly unyielding forces in the cosmos, the black holes, are not invincible. They are not forever. They, too, will end. This raises a question that stretches beyond physics and into the realm of the philosophical. If black holes are finite, then what does it mean for the entire universe? What happens to everything when even the most massive objects are subject to the passage of time? As if this discovery weren't enough, Hawking's theory presents another paradox. a riddle that has puzzled physicists for decades. It's a mystery that gets at the very heart of how we understand reality itself, the information paradox. According to the rules of quantum mechanics, information cannot be destroyed. In the quantum world, every particle's properties, its position, momentum, and state, carry vital information. The very foundation of the universe is built on this principle, that nothing is ever truly lost. And yet, if Hawking radiation is real, and if black holes evaporate, it seems that the information inside them could be lost forever. Once it crosses the event horizon and is swallowed by the black hole, that information might never escape. This is not just an intellectual dilemma. It is a profound question about the nature of reality itself. How can something as fundamental as information be erased? If the laws of physics, especially those that govern quantum mechanics, are to remain intact, this paradox must be resolved. And yet, here we are, left to contemplate the possibility that the very foundation of our understanding of the universe may be fundamentally flawed. For decades, the search for a solution to this paradox has been a driving force in the world of theoretical physics. Could the information be encoded in the radiation itself, hidden within the fine details of Hawking radiation? Or might the key lie in the surface of the black hole, on the so-called event horizon, where information could be stored in ways we don't yet understand? Scientists are looking at new and bold ideas, such as the holographic principle, which proposes that our three-dimensional universe might be an illusion, with information encoded on the two-dimensional surface of space-time. It's an idea that could change everything we know about the fabric of reality. And yet, despite the many tantalizing theories, the answer remains elusive. The search for an answer to the information paradox is far from over. But the pursuit itself is just as important as the answer. Every theory, every experiment, brings us one step closer to understanding not just black holes, but the fundamental workings of the universe. Perhaps the most profound implication of Hawking radiation is that it forces us to confront the idea of impermanence, not just of black holes, but of the very universe itself. Just as stars burn brightly and then fade away, so too do the black holes that once seemed invulnerable to the ravages of time. If black holes can evaporate, then what of the universe as a whole? Is there an end to the cosmos itself? We are left to ask, what happens when the universe's most enduring features, the stars, the black holes, and even the very fabric of space and time, begin to fade, to shrink, to decay? Does everything ultimately succumb to the cold, empty void of entropy? It's a question that stretches beyond the realm of physics and into the deepest parts of the human psyche. The discovery of Hawking radiation is not just a challenge to science. It is a reminder of our own impermanence and of the fleeting nature of everything we know. The universe, in all its vastness, is not infinite, not permanent. It is a place of constant change, decay, and rebirth. And in this ever-changing cosmos, we too are participants in this cosmic dance. Hawking radiation is more than just a scientific discovery. It is a window into the heart of the universe, one that reveals the fragility of even the most powerful forces in nature. It calls us to question, to seek deeper answers, and to embrace the profound mysteries of existence. As we continue to explore the far reaches of space, we are bound to encounter more mysteries, more paradoxes. But it is in the pursuit of these answers that we find our greatest purpose. We may never fully understand the secrets of the cosmos, but the very act of searching is what defines us. In the end, perhaps we are not meant to know everything, but we are meant to ask, to explore, and to marvel at the vast, unknowable beauty of the universe. For in that search lies the very essence of what it means to be human.